There is a specific throughput limit where traditional software engineering hits a point of failure. When information reaches a certain velocity and volume, legacy database architectures cannot sustain the load. For decades, the baseline standard has been the Relational Database Management System, or RDBMS. These systems rely on highly structured tables and rigid predefined schemas, designed for enterprise environments where data is measured in neat, manageable gigabytes. When an RDBMS needs more capacity, engineers rely on vertical scaling. This involves upgrading a single centralized server by adding more CPU cores and RAM to the existing motherboard. However, a single machine is bound by its physical motherboard slots and bus speeds. At petabyte scales, the ingestion of unstructured real-time data exceeds the hardware capacity of any one server. Modern information flows quickly outgrew these hardware constraints. Reaching this physical limit forced engineers to move away from single-server relational systems and design a different architecture. The engineering solution to these hardware limits is the Big Data Management System, built on the NoSQL model. Instead of relying on one massive server, NoSQL utilizes horizontal scalability. This distributes the storage and processing load across a cluster of hundreds of commodity machines working in parallel. Operating at this scale involves schema on read. The system ingests massive amounts of raw, unstructured data immediately, applying a structural schema only when a specific query is executed. This table outlines the distinctions. RDBMSs are categorized as relational and vertically scalable. NoSQL databases are non-relational and scale horizontally. The trade-off is how users interrogate them. SQL executes complex, multi-layered queries, while NoSQL schemas lack deep relational power. Moving away from the structural safety of rigid SQL tables is the price for a system that can ingest petabytes of varied data in real time. To organize this distributed information, engineers use data modeling. This is the architectural blueprint defining how data elements are stored, connected, and accessed across a system. This text shows the legacy models. Early systems used hierarchical, parent-child trees, or network structures. The relational era introduced the entity relationship model, linking entities like a customer to an order, as well as object-oriented models. Modern big data architecture accommodates varied file formats. While tabular data might use a simple CSV structure, web applications rely on JSON, a text-based format suited for transmitting semi-structured data. In platforms like MongoDB, this evolves into document databases. As detailed here, MongoDB converts JSON into a binary format called BSON. Storing nested data in a single schemaless document removes the need for processor-heavy table joins to retrieve related info. For datasets defined by dense interconnections, like social media platforms, engineers deploy graph-based databases. This overview highlights the unique architecture. Graph databases store entities as nodes, and the connections between them as links. This design outputs real-time query results for complex networks, allowing administrators to update relationships without significant schema alterations. Modern big data models prioritize the agility of network relationships and nested objects over the strict tabular rows of legacy environments. Operating without rigid SQL schemas presents an operational risk. Without active management, a flexible, distributed data lake can degrade into an unsearchable data swamp. Organizations implement big data management techniques to maintain order across clusters. The foundational layer is data governance, ensuring data is used consistently. Further down, data quality management scrubs inaccuracies, while data security protects repositories from unauthorized access and loss. Once the pipeline is secure, it yields the final outputs. Big data analytics extracts hidden patterns from the repository, while predictive analytics applies machine learning to forecast future demand. Extracting truth from chaos requires the continuous engineering of a managed pipeline. High-velocity healthcare environments provide a clear test case for these distributed systems. Consider near-patient IoT medical sensors. They constantly stream a high-velocity feed of unstructured vitals, like continuous heart rate readings, directly into a cluster. As outlined in paragraph 7, the big data system analyzes this telemetry in real time. If a physiological parameter crosses a safety limit, the system triggers an alarm, alerting a doctor to take immediate action. A traditional SQL database attempting to batch process this telemetry would introduce fatal latency. Only the velocity of a distributed big data architecture allows for these life-saving alerts. This architecture is equally critical for handling extreme data volume, such as the macro-scale inputs generated by the energy sector. Look at paragraph 9. Smart electric meters record power consumption every 15 minutes. Across an entire city, this generates millions of continuous data points streaming into centralized servers. The management pipeline analyzes this volume to forecast citywide power loads. It then issues recommendations to industrial manufacturers on when to run their heavy machinery to avoid straining the local grid. Moving from rigid tables to dynamic, managed pipelines marks the transition from simple record-keeping to a system capable of forecasting the future.